Hi, let's do some calculus. What? Let's do this thing. We're in daily lessons 175 through 177, and we're going to be talking about properties of definite integrals. So definite integrals are, we're thinking like antiderivatives, but where we can think area under the curve of a function like f of x, but definite integrals means there's a stopping place, or a starting place and a stopping place. So let's do this one. If I'm talking about some function f of x on a graph, this is f of x. So good. I know. And I'm saying I want the area under the curve, but I want to start at A and I want to end at A. How much ground have I covered? Like, how much area is there? None at all. So if you see anything, an integral starts and stops at the same place. If I'm talking about the area under the curve, there isn't any. So, and it's always the curve f of x. It's whatever's in the integral. If I would do the antiderivative and do f of b minus f of a minus f of a is still going to be 0. So, and we're talking about capital F of a minus capital F of a. So this is 0. Given that a is less than c is less than b. So in this one, what it means is a is less than c is less than b. So I've got something going on like this as far as an x value is concerned. If that's the case, if I find the area from, let's say, here to here, and then I find a different area from here to here, I can break it up and add those two areas together. So I can break this up into two integrals and say, well, this would be the area from a to c of f of x dx. Really important that you have this dx, because if we're talking about rectangles, for instance, this would be the height of one, this would be the change in x. Like, we need both parts of that. And the integral, we're adding up all those rectangles. So in this one, we've got this integral from a to c, plus, now I'm going to go from the rest of the way, c to b, same function, and that's it. But I can totally split up integrals in that way and add each individual part. If I have this, where I have this integral from a to b of f of x dx, and I get k. So let's say this. So I'm going a to b, and I still have this function f of x. Then, so if I go here, and it's all above the x-axis, I'm going from a to b. Right now, I can tell you that this is all going to be positive because I've got area above the x-axis from a to b. But what if I switch those and I said, you know what, instead of saying the change in x is from here to here, I'm going to say it's from here to here. That would make it negative. It would switch everything around. So if you ever see these two switch, this is a lower number, this is a higher number, that's how it should always be. This is the lower limit of upper integration, lower limit of integration, this is the upper limit. And if I switch them, this is the same outcome, except now I have this negative. So it switches from being positive to negative because I switched the order. So if this is BA, it's just going to be the negative value of that. Okay, this one says given B is less than A. And this one, oh wait, sorry, I messed this up. This one, I kind of should have just written this down here. This one's saying if a to b f of x dx is equal to k, if I switch those two, sorry, I got really excited if you're using pen. You also like to live dangerously. Actually, I don't like to live dangerously. I like using a pencil, but I'm living dangerously because I want you to be able to see it. I like that even more. So I'm putting negative k because I knew this was k. If I go down here and it says b is less than a, so you see how right now b is less than a, I should be putting this down here. I switch them and I make it negative. So same idea of what I just said. This one is a is less than b. I would switch it and it would go the opposite. So, okay, hold on, let me do one. B is less than a. Okay, so we have this function, we get the area. If suddenly I go a to b, then this would just be negative whatever I got the first time, b to a. Okay, if we do this next one, this, if k is a constant, we actually did this a little bit already in that last practice, but if k is a constant, we can put it out in front and just bring it along for the ride. In this one, if I have this integral and I'm adding two functions together, we actually did this a little bit on the last page too, where we had like f prime and we had f double prime here. We can split this up into two. So I can say this is f of x dx, find this integral, plus or minus the integral from a to b, so I just write that integral symbol again of g of x dx. Given that f of x is an even function, so even functions are reflected across the y-axis right here. So I can see if I'm going, let's say, from a to b, or this says negative a to a. So let's say a is over here, and I've got the same place but negative over here. The area, some people will automatically like fill this up. Don't do that. Remember how we draw this is we do a horizontal line. This is f of x, by the way. And then we go up on the endpoints until we hit the function. So we're talking about this area. Do you see how it's the same on the left as the right as long as these are the same and it's an even function? Well, this is just going to be twice whatever happened from 0 to a. So you take whatever this area is and we double it. I could have said the same thing from negative a to 0, and we take 2 times that. In the next one, if this is an odd function, and again this is f of x, because it matches here, this is how we can talk about the area under the curve. And now I'm going from negative a to a, so same distance on both sides. Remember how I draw this is a horizontal line. I go down on the left till I hit my function. Here I go up, and I've got this area. It looks like the area is the same under the x-axis as above. So what do you think this will be? 0. Because anything below the x-axis, the area is negative, above is positive. Do you want to do more? Let's do more! Go to 176. Okay, so I've got some information in this one. That's nice. A lot of this is just practicing, so practice as much as you can without me and use the video as needed. So 0 to 3, this says 3 to 0. So let's think about this. Okay, if 0 to 3, f of x is equal to 6, this one is backwards from that. So what do I do to the answer? And it says determine, the property of integrals, explain how you arrived at your answer. I'm just going to write it out. So I'm going to write, well, I know that this would just be whatever's flipped. And I make it negative. And you can always go back to the previous page. Be like, where did we see that again? Oh, it was right here when I flipped these two that I can make the other one negative. Did I even show you? Could you even see what I was doing? Ooh, there we go. And this one, number 4. Okay, so this one would just be equal to negative 6 because I know what 0 to 3, the integral from 0 to 3 of f of x dx is. Okay, what do you think for 0 to 7? Well, I know 0 to 3. And I also know 3 to 7. So this is me explaining my work. And now I can just say, well, what is the integral from 0 to 3? It's 6. The integral from 3 to 7 is negative 8. Get an answer of negative 2. What about this one, 3 to 3? I don't see anything up here that says that. I can't have an area of a region if there is no region, like there's no change in x value. So this would just be 0. And you can put this if you want, you know, just so I know that it's always from the same thing. But this is enough to just say 0. Okay, next one. Ooh, this is fancy. It has 2 things at once. So here I've got this 3 that I can bring out in front. But I also want to switch this. Do you see how this is 7 to 3? What if I switched it 3 to 7? Yeah, bring a negative out in front. Three to 7 I know. 3 to 7 is negative 8. I'm using properties of integrals. I'm showing my work. This one I would say is the most commonly missed of any problem when I traditionally do this with students. So you try it and then come back and work through this with me and make sure you do all the steps. Okay, I'm going to break this up into two parts. And I'm going to guess that you got the second part. If this is 3 to 7, this would be -8. What is harder is this part. And there are two ways that you can do this. You can think about, well, what does the graph y equals 2 look like? It's a line at y equals 2. And if I'm going from 3 to 7, the area under the curve, like between y equals 2 and the x-axis, would be a distance of 3. 3 to 7 would be 4. 4 times 2 would be 8. And you could do it that way. Or the other way that you could do it is you could say, well, no. Fundamental theorem of calculus says I can take the antiderivative and I can evaluate this from 3 to 7, which would be 2 times 7 is 14 minus 6. Hey, I still get 8. So you get 18 minus 24. Whew, tough one. My chair is so squeaky. Let's keep going. This one says from -3 to 3 of f of x if f of x is an even function. Well, remember on the previous page we talked about even functions. And we said it was just going to be double the area. So I've got from here and here, it's the same thing on both sides of the x-axis. So I'm just going to say 2 of whatever 0 to 3 is. Because I already know that. It looks like I have -0. I didn't mean to. I wrote -3 first. So this is 2 from 0 to +3. So 2 times 6. Okay, next one, if we have an odd function, remember what happened. As long as we're going from -3 to 3, you should get 0. And if I'm explaining this, you can just say because this is an odd function or any value, so -a to a. Or any odd function. Okay. Do you want more? Thought so. Look at that. This kind of looks to me like if you had Darth Vader, but you had him like in the form of a bobblehead or something. Look at that. Doesn't it kind of look like it? I don't know. Or maybe like what's that thing you play badminton with? Like the shuttlecock things that you like hit over the net. Kind of looks like a birdie. That's what it is. Yeah. Okay, anyway, let's do this. So it says picture to the right is graph of f of x. I'm going to label it. Because right now it's not labeled. That's not good. Now it is. So much better. This is saying what is the value of this integral 0 to 3 f of x dx. In this one, I can see if I want to find this, do you see how I've got f of x and it matches? Anytime you've got two things that match it on an integral, like you've got a graph that matches this integral, like the integrand, the stuff within the integral symbol, the f of x, you can take the area under the curve. So I'm going to go from 0 to 3. So 0 to 3, you might want to write this in pencil because we're going to be messing with this quite a bit, but I'm writing in pen. If I go from 0 to 3, I made a horizontal line. If I go up on the left until I touch my function, here it's already there. I'm talking about this whole region. So this might not look like shapes that you know, but it is. This one is a quarter of a circle. Down here we've got a trapezoid, or if you want to make it even nicer to do, they've got a rectangle and then a triangle. We're talking about this whole region though. So we need to add all these areas together, but it's totally fine to break it up. If you want the area of a circle is pi r squared. If you thought it was 2 pi r or something else, that's circumference. But you might want to write this at the top. This is one you need to know. Area is pi r squared. So this one I'm taking 1/4 pi, because it's only 1/4 of a circle. The radius is 2, plus I'm going to add this area of a rectangle, which would be 2 times 1, I get 2. Plus this one, I can see from 2 to 3 would be 1 unit, this is 0 to 1 on the y-axis, so I've got, this would be 1. This region though then would be a half. I put all this together. 2 squared is 4 times 1/4 is 1. I get pi plus 2.5, or I can say 5/2. We did it. Let's keep going. What if I extended this region, and I know that from 0 to 3 is this. If I extended it just a little bit more. Do you notice anything about this region? So now I've got this part included also. Well, you might be noticing that this area and this area cancel out. A common mistake would just be take this, subtract 1/2 from it, but that doesn't do it because or actually, would that do it? We're adding a half and we're taking a half away. That could be, people do weird stuff on this though, whether they counter this one or not. So let me add this. I would do, this region we said was pi. This region we said was 2. I don't know. People do weird things on the end of this. I'm not sure exactly what it is. And then that's it. We wouldn't include both of these because one is positive, one is negative. I can't remember this mistake people make. They do something else with this where so just be careful. Go back through it in your head, what you have to do for that one. Okay, this one I'm going to go -3 to 3. So I'm going to get fancy and pick out another pen. Notice this f of x still matches up here. We've got to be careful. F of x, we're still good. This one I'm going to go for the whole way from -3 over to +3. So it would be this entire region. Well, I knew from 0 to 3. What do we know about that? From just 0 to 3, I got pi plus 5/2. On the other side, I'm going to have the same thing. So I can double that. This is an even function, so I should get 2 pi plus 5. Okay, 2 more. So switching gears though, this one says if capital F of 0 is equal to 5. Capital F of 0, that's antiderivative language there. What is the value of f of 3? Oh, these are such good test questions on ones like these, where f is the antiderivative of f of x, lowercase f of x. Okay, the only thing I have here is f of x, lowercase f of x. As soon as I know I need to get back to capital F of x and I don't have a graph, you should be thinking, I'm writing some stuff with the antiderivative, because I know I need to get back there. Fundamental theorem of calculus says that if I take an antiderivative, I can do f of b minus f of a. So that at least gets me in the right realm. In this problem, I know f of 0 is 5, and I want to know f of 3. So I'm going to use this x value of 0 and go the whole way until I get 3. And then over here I can put capital F of 3 minus capital F of 0. Then this becomes just a fancy equation if I'm solving for what I don't know. So in here, 0 to 3, we already did that a couple times. We got pi plus 5/2. On the other side, f of 3 is, what do we say f of 3 is? Do we know that one? Oh, we don't know. That's what we're solving for. But I do know f of 0 is 5. Add 5 to both sides. Pi plus 5/2. I'm just writing plus 5 for right now. 5 would be 10/2, so this would be 15/2. Okay, one more like this. You try to set it up. Again, because I have a lowercase like the graph of lowercase f of x, the only way I can get to the antiderivative is by integrating. Fundamental theorem of calculus says f of something minus f of something, capital F of something. I'm going to go from, this is -2 to +2. And then I solve for the things that I don't, or I plug in the things that I know, solve for the things I don't know. So from -2 to 2, have we done this one yet? I don't think so. From -2 to 2, this would be this region. So it would be this guy right here. So it'd actually have half of a circle, sorry, 1/2 pi. The radius of the circle is still 2. Plus the rectangle in this case would be 1, 2, 3, 4. F of 2, I don't know, that's what I'm trying to find. F of -2 is -2, so minus a -2, or I can say +2. If I solve this, this would be 2 squared would be 4, this would be 2 pi plus 4 is equal to f2 plus 2. Subtract 2, I would get 2 pi plus 2. Ta-da! I always feel like I need to say that at the end, or at least some other exclamation of some sort saying, we did it! Thanks for being great. Thanks for learning. Thanks for wanting to learn and showing up on days even when you don't want to. I appreciate you. Please ask me if you have any questions at all. Thank you. Bye.